So, hi everyone. I'm Ishkar from Plyops, and today I will explain how adding a new tier to the AI stack as a disaggregated, shared key-value storage can help make LLM inference more scalable and more cost-effective. Our work is inspired by work that was done both in academia and in industry in other companies, but it builds mainly on the key value store that was developed in our company. And I hope to explain and to convince you that indeed this is the best fit for LLM inference today in the talk. So earlier this year, Eric Schmidt, former CEO of Google, said that not only AI revolution is not overhyped, it is rather underhyped, both in terms of the opportunities that it brings to us and also in terms of the challenges, mainly infrastructure challenges, major challenges that we need to overcome. Now, we are in the last few years, obviously, as persons, as citizens of the world, have looked how LLM can help us in our personal day-to-day lives. But I think that we are, as storage and network companies, as part of the tech community, we also must think of how we can contribute to this revolution. And I think that actually we are very fortunate to be working in this era. It's amazing. I've been exploring this field for the last 2 years, and it's really the pace in which innovation come in is really overwhelming, and we shouldn't miss the opportunity to become very essential in the AI stack in this way. So, and I'm not just talking about feeding the beast or not being the weakest link in the chain. I'm talking about becoming really an essential component to the pipeline. Imagine an SSD walking into a GPU bar and saying, "Hey folks, can I help you with latency?" So it might be funny, but I think this is the reality, and I hope we can see it today. So as we all know, LLM applications are really growing rapidly, and they leading to like immense deployment of expensive and power-hungry GPUs. Eric Schmidt in his talk mentioned that there are countries that are now deploying 5 to 10 gigawatts data centers for serving LLM inference. That means each one is equal to 5 to 10 nuclear power plants. So that's really big. So obviously the main problem, number one problem, is electricity and the resources. And GPUs and the power that they consume is limited, and the compute power that is needed to serve LLM inference often exceed the supplies, leading to the fact that in many cases user requests are denied or served without meeting the SLAs, violation of SLAs. For example, the time to first token, or the time per output token, which captures the interactivity of the system. So our goal is to build solutions that increase the efficiency of existing infrastructure, and that should be both or either in a higher performance per watt and better user experience per dollar. And the question is, can we achieve both? It's challenging. Or put in other words, our goal is to serve more queries with larger models, faster, all under the same power budget. Okay, so let's take this goal and keep it in mind throughout the presentation. Now, in this room, most of us are engineers and scientists, so we don't like words like higher, better. We want it to be more concrete and formal. So for this, we have this diagram, this plot. The y-axis are the throughput, represented as the RPS normalized per GPU, and the x-axis are the latency of the system, captured as TPS normalized per user. So what this plot captures is the tension between the system efficiency versus user experience. So you can see, and this is the result of actual experiment that we ran. So you can see that when the throughput increases, then the latency both in terms of user interactivity and the time per output token is getting lower. While if we want to improve the user experience, there is a limit on the traffic, the amount of traffic that the system can serve, and throughput becomes lower. So we are always in this tension between satisfying these two requirements. And the best that we can do is actually to push this curve outward, right? So we want to have consider a specific SLA that you define for the system, let's say 25 tokens per second. We want to get higher efficiency per that specific SLA. And this is exactly what our solution provides. So, okay, so far we've explored or defined the challenges that we have in LLM inference. And the agenda for the rest of the talk is first to explain why Prefill and KV cache are so dominant in the gaining end-to-end performance. Then I will describe the shared KV cache approach for offloading the KV cache into disaggregated storage. And in between, I will have some theoretical analysis and results showing, analyzing the model that we present and the implication on system design. So let's dive in. First, let's try to understand why at all LLM applications are so costly or so heavy. So, you know, many popular LLM applications actually have repetitive context, right? The first example would be chatbots that, as you know, that they reuse your earlier history, your earlier conversation history whenever answering your following answer. So this way, the context, the prompt is growing each turn. Likewise, backfixing systems are analyzing entire repositories, code repositories over and over again. And personal assistant bots are continuously querying and analyzing and reading a big set of documents in a data set that can be either proprietary or like the personal history of a person. So this repetitive computation is obviously highly inefficient, right? We have some researchers say that up to 99% of the prefill costs are done by repeated computation that already been done in the past, and this obviously a huge waste of the GPU resources. But worse, the fact that we have to meet the SLA, having these longer periods of time to run the prefill, limit the HBM utilization and the end-to-end gain by limiting the batch size that we can serve. And this is even crucial, more crucial than the prefill time that it takes. So let's zoom in to understand how exactly LLM inference is working. So it basically can be separated into two main phases. The first phase is a prefill phase, where we process the entire prompt that was given by the user. And the main responsibility of the prefill phase is actually to build the KV cache tensors for the second phase. Okay, so it also generates the first output token. So it is measured by the time to first token. This is TTFT, is the metric by which we measure the prefill. And it is usually between 400 milliseconds to 1 second. And this phase is compute bound. So as we have longer prompts, longer context, it takes more time. The second phase is the decode phase, where you sequentially generate token one by one. And it's memory bandwidth bound, because it spends most of the time loading both the model memory and the KV cache tensor into the GPU SRAM. And the metric that we use to measure it is the time per output token, TPOT, and it is usually between 40 milliseconds to 100 milliseconds. Just to make sure that we understand and we're on the same page, when I say that decode takes the most of the time is unloading the memory into the SRAM GPU, that means that it happens on each decode step, right? So for every time that you generate the token, you need to reload the entire memory of the model into the SRAM. There is simply not enough space to hold the entire memory, so you hold it and evict it and load it again, and that's but that's not a thing that currently we see how we can optimize. So now that we've focused on a single turn, how we run the prefill and the decode in LLM Inference, now I want to zoom out and discuss the multi-turn sessions, use cases that I've described earlier. So what we can see is that between each turn, the prompt is getting longer, and so the KV cache is also getting bigger and more time to compute. So between turns, so we have the first question and the first answer. But until the second question arrives, usually the KV cache is being evicted. Simply there is not enough room in the HBM to serve all the active and pending requirements, so some of the KV cache needs to be evicted from it. And then on the second turn, you need to recompute the prefill, although it was already computed in the first turn. So in our example, Q1 and A1 are recomputed overall 3 times in 3 turns. And this is a huge waste of the GPU compute cycles. And this is really the aha moment for storage people, right? Because KV cache offloading has a very simple idea. Instead of discarding the KV cache tensor from HBM, we can reduce the time to first token simply by moving them, writing the KV cache tensor into some KV cache store. Okay, so there can be several types of KV cache stores, and I will elaborate about this later on in a later slide. But in our case, we're offloading the KV cache tensor into our KV store, our Lightning AI box. And what we can also see here in this picture is that the KV cache tensors are generated in very small chunks during the decode phase. And in order not to become the bottleneck of the system, they need to continuously be streamed into the KV cache stores. Okay, and they are very small as it is, and there are several optimization techniques for those who are familiar with it like GQA, quantization, that make them even smaller. So it's very important that the KV store is able to handle a large amount of IOPS, of small random IOPS. Okay? This is an important characteristic of the KV store. So what makes our solution unique? So first, it supports GPU-initiated I/O into a disaggregated KV store. So GPU-initiated I/O was just described in the earlier talk, happily for me. And what I can say is that all the intelligence that was described in the previous talk is already inside in our solution. And actually, as CJ also mentioned in the previous talk, GPU-initiated I/O was incepted and implemented by NVIDIA. And what we did is actually to extend it to support KV API. And so if you're here tomorrow, CJ and Wenmei have a session in which they will, I'm sure, will tell about their vision for GPU-initiated I/O, and I'm proud to say that we're also proud of it. We are also part of it, as we've extended it to support a key value API, and you need to understand that this is very important because key value API is very flexible and makes it a very strong building block for this specific stack that I'm presenting here, but also for other use cases and AI use cases that are not presented here. So our solution supports variable size, seamlessly supports compression, and is able to saturate the fabric with small random I/O, and without the intervention of the CPU in the critical path. What was presented implicitly in the previous slides is that we actually need to do three things while we're doing the prefill, right? We need to retrieve the past token that was already computed, to compute the new interaction for which we still don't have the KV cache, and to store the new KV cache. So what was presented in previous slides, and now we'll say it explicitly, is that the KV cache tensors are managed at the layer. At each parallel layer manages its own KV cache tensor. So this allows us a perfect overlap between I/O and compute. So, and this is what this slide demonstrates. So, for example, when computing the KV cache, the new KV cache of layer 4, at the same time we are prefetching the KV cache for layer 5 and writing the KV cache that was generated in layer 3. And this is all possible with our async GPU-initiated KV I/O. We have two GPU-driven architecture. The first is a clean GPU-initiated I/O architecture that uses a DPU, smart NIC, like the NVIDIA Bluefield, in order to pass the I/O from the GPU in the initiator node into the storage in the target node. So the DPU here serves as just emulate an NVMe device, and therefore allows us to move the GPU itself to initiate the I/Os and to use the RDMA to bring the data directly from the HBM of the GPU to the target, through the NIC, to the target nodes, and also backwards directly to the HBM. A second architecture that we implemented in case our customers don't have a DPU in their environment requires us to have the CPU to be part of the pipeline, because now we lost our ability to have the NVMe device emulation. So we have a KV gateway component that does all the network stack software that was previously done by the DPU. And we have the CPU here preparing the metadata, I don't know, allocating buffers and doing some stuff. But still, the GPU is the one that triggers and defines the timing in which the I/O is triggered, and also does the synchronization. And we need very light synchronization because we control the solution to know when exactly to wait or not to wait for a specific I/O. So we've described our solution, in general, the approach and our solution and architecture. But now the question is, when exactly does this approach pays off? What are the conditions, or the system conditions, or the workload condition in which I/O are outweighed GPU recomputation, right? So for this, we have a theory model. And and we start just simply by modeling the prefill acceleration, just understanding how we can measure the prefill acceleration. So this slide defines like basic terms that we need to have the analysis. We have R, the time to retrieve the token from storage, T, the time to compute a single token in the KV cache. The effective token acceleration, we mark it as E, which is, of course, the ratio between these times. And alpha is the hit rate, the KV cache, that fraction that is cached in storage. And as you can see, R depends mainly on the bandwidth of the I/O, while T depends also, or mainly on the model size, the KV cache size, the length of the KV cache, the length of the input, and also the compute power of the GPU. So obviously, if we want to compute how much time to first token of a simple, of the vanilla solution would take, it would be T times the length of the input. But when we consider the KV cache offloading, there are two parts that we need to consider. We have the time to retrieve the old KV cache, which is alpha. Its portion is alpha. We have the time to compute the new KV cache, and also the time to write the new KV cache. Okay, so luckily for us, when we are able to overlap the I/O and compute, we can just take the maximum from all these terms, right, and not to add them all up. So, and when we are, the first insight is actually that we see that the write and the compute have the same structure. And if we know that write matches the compute time, which it usually does, then we can just eliminate this term from the equation, and we are left with two elements. One's describing the time to retrieve the data, and one that describes the time to compute the data. And now when we compare or divide these two terms, we see the speed up that we can get. And we have two regimes. One is compute bound and one is I/O bound. Obviously, when compute takes more time, then we're compute bound, and this is the ratio in which we can speed up the computation. And when we are I/O bound, this is the ratio by which we speed up the emulation. Now, let's see these two formulas just visually. It would be easier to understand. So what I have here is on the x-axis, we have the ratio, the hit rate, alpha, that goes from 0 to 1. And we have the two graphs that are representing the speedup, both in case of I/O bound and compute bound. And obviously, the real speedup is the minimum between the two. So, and we mark here by alpha star the point in which we turn from compute bound to I/O bound. Okay, it's an important point. And also, I want to mention that this specific graph was created for E equals 9, meaning it's retrieving data from storage is 9 times faster than computing the token. Okay, but obviously it can change if E is different. So two insights that we get from this plot. So first, once we are in the compute bound regime, I mean that is defined by the heat ratio and the factor E, the factor by which we can speed up the computation, there is no need for faster I/O because we are already bounded by the compute. So replacing the SSD, the SSD storage with HBM and DRAM won't help us. Okay, so this is a first interesting insight. And the second insight is regarding the I/O bound. Now note that maybe it's hard to see here, but you can see the overall trend that it's getting lower as the heat rate increases. So our way actually to maximize the speed up is not to use all the KV cache that we have in the storage. We just need to stop at alpha star. That can be obviously just can be computed during inference time. So let's give a concrete example. Say that you have that your E is 9, so a retrieval is 9 times faster than compute, and you have 95 tokens out of 100 tokens in your KV cache store. It wouldn't be wise to bring all 95 tokens. Just bring 90 tokens and let the GPU compute the other 10 tokens. This way, you are compute I/O balanced, and you are optimizing the utilization of both resources. Okay, so here is the result of some tests that we ran. We compared our solution versus vLLM, which is de facto state-of-the-art, the best LLM inference that is currently out there. And what we did, we tested some model, I think Llama 70B on H100, and we increased we have different prompt sizes, and we set some SLA for teapot and for time to first token, and we simply increased the batch size until we meet the SLA. So what this gives us is a 7x prefill acceleration, obviously, because we bring the, I forgot to mention we have 90% heat ratio here. So we are 7x prefill acceleration, and this allows us to have higher batch sizes and still meet the SLA, which brings us to 8x higher end-to-end throughput gain. Another thing that we can see here that Speedup is an enabler for being SLA compliant in long prompts. So vanilla simply couldn't meet the SLA in the long prompt here, even with a single batch, a batch that consumes just a single request. So we're not just shrinking the time, but also enabling to run some of the workloads that are simply impossible with vLLM. So as I promised you, there are several ways to implement this KV cache offloading approach, and we classify them into strata. So the first strata is S0. It's simply storing the KV cache in HBM, which is simple and very fast, but obviously you have just a tiny capacity, and most likely KV cache tensors are evicted from there. S1 extends the capacity by leveraging both either DRAM or SSD, but it remains non-shareable between different GPUs and incurs higher cost obviously when you use DRAM. S2 now uses a shared namespace, and it's deep because it uses a disaggregated solution. But this is on the expense of either performance when you're using distributed file system, or cost when you're using in-memory key value store. S3 has all the benefits. It has a shareable namespace, it's deep, and it improves performance. And obviously, a PLAB solution is positioned here. Okay, so up to this point, we've discussed just a single instance of vLLM. And obviously, there are already solutions of data center scale LLM inference, for example, Dynamo by NVIDIA, LLMD by IBM, Google, etc. And this is a schematic view representing most of these solutions. So it has a single centralized router that uses some mapping of the KV cache. It combines KV cache aware routing with some load balancing strategies. And of course, since it ties the storage where it keeps the KV cache with the compute, it's not scalable, and obviously you have the memory footprint for managing the KV cache mapping, and combining two different often different strategies for routing would result in non-optimal routing. What disaggregated KV cache offloading does is simply decouples obviously the storage from the compute. It allows to improve the scalability, elasticity, cache to be recoverable, supports PD reconfiguration, and has all the benefits. So it's very simple when you think about it. We just and obviously it simplifies the routing, because you just need to route by load balancing, and you know that the KV storage would bring you the KV cache wherever you need it. So you're delegating the I/O to the technology that is an expertise in managing the I/O, and you just leave the GPU to do what it's best at, which is the compute. So in multi-GPU systems, the prefill and decode of different turns are often computed on different GPU, as we see in this example. And this means that even if we have the KV cache for Q1 in this GPU, here we have to recompute it when we are in a compute-only system. When we have a disaggregated shared key value store, we can just bring the KV cache that was computed in any other node, and this makes cross-node operation very smooth and efficient. I mentioned briefly a case where prefill and decode are computed in separated pools, but and this comes to solve some of the performance issues that we have in LLM inference, but it has its own disadvantages. So let's consider the case where we're collocating prefill and decode on the same node. So obviously now when we have continuous batching, we have some interference between different requests. So if we have two decode steps that are batched, then that's okay. Decode steps love to be batched, because anyway they are memory bandwidth bound. But if we're batching prefill or prefill decode, then we have interference that creates this bubble that delays our execution. And actually, KV cache offloading also helps us solve these bubble issues. So let's see if we can analyze this and model this and see exactly how much gain we can get from KV cache offloading for continuous batching. So obviously, B is the number of concurrent requests. This is the batch size. But obviously, the number of prefill that are now batched is much smaller than B, right? So consider these are the execution of, let's say, B is equals 5. So when this is different requests that are running concurrently. So in some of the slots, we won't have prefill step at all. Some of the slots would have one prefill. Maybe seldom will have two prefills, but almost never 3 or more prefill in a single slot. And actually, the number of concurrent slots follows a binomial distribution that depends both on the batch size and the amount and the size of the output, the average output size. So we still want to be able to analyze and capture what is the potential acceleration for prefill and end-to-end gain. So I'm not going to go into all the mathematical details. This can be done offline. But what we can see is that first, that the time to first token is not simply B times the time to first token of a single request, but it's more involved. But we also see that the time to first token also cascades into the computation of the teapot. And we see here exactly how it affects it. So we are affected by the number of time to first tokens, by the time of prefill that are executed concurrently with the decode phase. And also the fact that we increase the batch size also contributes to the time that we load the KV cache into the memory. So let's again see it visually. We have here in purple the time that is measured for what we call a basic teapot, when we average over all the teapot steps that don't have any concurrent time prefill with them. And the light blue is the time that it takes for a teapot, the average teapot. And you can see here the gap is exactly due to the effect of time to first token on teapot. And this is the gap that we would want or be able to close if we reduce time to first token. So going very briefly on the analysis, as I mentioned, we have here when we compute teapot as a function of B, we have here the element, the incremental element that depends on the number of prefills that we have in concurrent, and also the incremental portion, the incremental part that depends on the time that we load the additional KV caches into a memory. And if we want, again, to meet the SLA and have the maximal batch size, we can see that the gain is actually depends on delta P over delta H. Now, plugging in the numbers would show that the gain actually depends on 3 major elements or components. First, the model parameters that are captured here, the GPU parameters that are captured here, and of course, the application parameter, the size of the input and the size of the output. So, for example, what we see here, and this is, and we're separated into a short prompt and long prompt regime. This is due to the effect that the time to store the data into the model, into the SRAM of the GPU needs to consider both the model size and the KV cache size, which is affected by the prompt size. Okay, so at some point, the KV cache size is the major part of the parameters that we are loading to the SRAM, and with a shorter prompt, the major most of the time spent in loading the model. So what we see here is that the ratio between the bandwidth of the memory bandwidth of the GPU to the compute power of the GPU affects the gain that we can get with KV cache offloading. And for this reason, for example, we can bring much more gain for models that run on H20 versus models that run on H200. Okay, and there are more interesting things here, but I don't have much time. So just want to wrap up with a visual view of the improvement in continuous batching. We compared here Dynamo, which is NVIDIA's a data center solution for LLM inference, running prefill and decode collocated on a single node or disaggregated on different node. And obviously, we took the best performance for Dynamo versus our solution Dynamo that uses our solution with KV cache offloading. And we can see that no matter, the gain varies when we consider different points, but no matter where we see a major improvement in the trade-off between system efficiency and user experience when using KV cache offloading. And this is exactly what we wanted to happen, right? Pushing the trade-off curve upwards. That's it. This is all I had to say. I'll just recap some of the major insights that we saw in the presentation. So first, KV cache offloading increases efficiency and reduces cost while maintaining user experience constraint. Throughput gains depend on the model, the GPU, and the workload, and we actually have a well-defined formula to estimate what would be the gain. In compute-bound cases, which is actually really the majority of the cases, there is no benefit for faster than SSD memory solution for KV cache offloading. Speedup depends mainly on read performance and GPU-initiated I/O, overlapping compute and I/O asynchronous, I/O zero, CPU overhead, key value API are all crucial for getting higher performance and better efficiency. That's it. If you have any question, I think we have time.
your case, you had all the optimizations, overlapping compute, storage, X amount of hit rate, and not really reading part of the data, but computing it to optimize and all that, right? And I assume you also had GPUs and neural fabric using RDMA for accessing from your storage. What was the equivalent with UPLL? Was it a local SSD?
No, vLLM doesn't support. Oh, yeah. So the question was about our comparison for our solution versus vLLM. And vLLM has a feature that's called APC, where it can store, it doesn't evict the KV cache from HBM if it doesn't have to. But it doesn't have, like, natively any support for KV cache offloading. So obviously, the comparison is exactly what we wanted to compare. What happens when you recompute the KV cache versus what happens when you bring it from storage.
One more question.
Yeah.
So, the last slide you had comparing Dynamo, right?
Mm-hmm.
Which I assume brings in some of these for vLLM. Is that?
No, what was the question? The Dynamo? Dynamo, okay, yes, Dynamo runs, here Dynamo runs over vLLM, and you're right, I forgot to mention it. Obviously, all the storage, all the data center solutions can run over, they use as a core element some inference engine, so it can be vLLM, SGLang, TRT-LLM, and in our experiment, it was vLLM, Dynamo with vLLM. Yeah.
Do you have any data on the size of these prefill blobs, for want of a better word? Like in terms of like how big are they, distribution? Just trying to get a sense of how big they are.
Let me see if I have. Yeah. Okay. So the question if we have like an estimate of the size of the entire KV cache.
Of the prefill that you're filling in. So when you do a storage I/O,
Okay.
like typically what's the distribution on size?
Yeah. So obviously the vLLM and also other inference engine manage the key value tokens in blocks. So it can be 32 tokens, 64 tokens. In some cases, it's just a single tokens. And we write to the storage exactly these blocks. And we can aggregate more than a single block, but it's roughly a block. So the I/O that we generate depends only on the size of the block, and so we control it. But if you're asking about the entire size of the KV cache, so obviously this depends on the workloads, and you have prompt of 32K or of 500K, and we have like requests from customers for all sorts of sizes, and it's just a matter of math. You can just compute it. But what this table shows is the size of the I/O that we're doing, and what are the performance requirements that are needed in order to support. This is running, I think, DeepSeek on H200 or something like that. Yeah.
You mentioned earlier that when writing those blocks for creating new tokens, that those would be random writes. Why would those be random instead of sequential appends?
Okay, so okay. The question was why we consider the writes from the KV cache offloading to be random writes and not sequential appends. I assume you are assuming that you're writing to a file, and even then, it's not really. You create sequential writes only if you're writing very big segments of data. If you are writing them here and there, they won't be sequential, right? So you're generating like these batches of 32 tokens, and then you're writing them. And the rate in which you generate them and write them makes them small, and hence they are random. You need to, even if you're appending them, where would you append them, right? So either you batch all of them and write them as a single segment, and then they will be sequential. But even then, you need to still understand where exactly they are located and map to them.
From the application perspective, though, when we generate a block that's associated with a query, and then we have the next block that's also associated with that query, those are considered sequential because they would likely be used together, right? So the difference between whether or not it today ends up random writes versus is that an opportunity for optimization, it sounds like it is an opportunity for optimization because there is knowledge in the application that these go together.
Yeah, so the question was there is an opportunity for optimization because the blocks of the entire, at least in the entire prompt, and then the entire decode, and then again the entire prompt are then maybe retrieved all as a single block, and there is optimization for writing them also sequentially. Well, I didn't mention it because it's not in the scope of this talk, but when you think of future and really now already existing use cases, it's going beyond prefix. You can't always assume that you are going to retrieve the entire prefix of the query. There are several applications that you would actually need small pieces of your history to retrieve them and use them, and you can maybe even change the order of the chunks that you need to retrieve. And they are now becoming even more and more common, and would probably will be even higher than the prefix portion of the LLM application. So long answer for saying that you can't assume that the way that you would retrieve the KV cache from the storage would be sequential as you produced it. Hi. Wait, I don't think that I quite heard it. The performance of the storage depends on what?
If you, for example, have many different tenants, many different users within your request, right? Files, I guess, files, you will get one latency, one bandwidth, right, per specific stream. But then if there are other tenants there, you might be getting significantly lower performance. Without loading all of those given values, it will take forever mass interaction for you to adjust all the code.
First of all, so the question is there, if the storage time can vary, and to the point that it's actually more efficient to recompute. So first of all, when you consider storage time retrieval, you usually consider like the worst time, what it would take when the system is saturated. Right, and obviously you don't want, if you're bringing your system into a saturation point, then you probably need more storage or more XDP, in order not to degrade the performance of the storage. Yeah.
And the second question, so it looks like in the use cases that you described, people inside chat or certain data, certain KV values at some point of time is not going to be kind of not the key is going to not happen just because the chat is over, rather than document all the questions about the document or asked by that user. Do you guys support something like eviction, complete eviction from files?
Yeah, so the question is about the eviction and about different use cases where the data essentially becomes cold and should be evicted. So yes, obviously we have smart eviction policies, but since we are an SSD company accelerating the SSD, the assumption is that you can have such a huge volume of storage compared to DRAM or anything that could be that you can save much more history. But obviously you need to be very smart on which key value exactly you are evicting. For example, if you consider it like a chain, like a sequence, you would want to evict like the last blocks and not the first block. That would eliminate the way to serve it as a prefix. And yes, obviously we support it. Yes, I think we have time.
No, I think we need to move on to the next.
We need. Okay, so thank you. We can talk offline.